H2O and H2SO4. Can this add? Someone is saying yes. Could it add? Could the H2SO4 water, acidic water, add onto a double bond? Yes. So then nothing stops it from adding onto a triple bond either, right? No? Come on. Yes. We showed you water addition, acidic glycemic alcohol, anti-wave, Markovnikov on a double bond. Nothing stops the alkyne, which is another pi bond there, two pi bonds, from reacting with this water, right? So this is an interesting one. Before I go there, I want to show you some of Bruce's images, and maybe you can visualize this better. So you see how here we talk about addition of HCl or HBr on a triple bond, and we talk about hydrogen and chloride being added from opposite side. I'll show you the whole thing. Anyway, so they propose that this is sort of intermediate. The intermediate is really this kind of a ring, right? What does this remind you of? Bromonium-like, right? Bromonium-like or mercuronium-like, and then if that happens in that moment, then the chloride can always attack from the bottom on either of these two sides, and then it can give you rise to this hydrogen chloride being added to the opposite side of the double bond. Basically, this happens to be a Z product. Okay. Yeah, so this one we went through, and you saw that the bromide adds onto, that was last time. This is the drawing I didn't have last lecture, which is when the first on the alkyne, when you're trying to add HBr, so you add a hydrogen, you add a bromine, and you make a double bond. So like first equivalent, you make a double bond. The question is, if you have a second HCl, where will that go? And that goes actually, the chloride goes onto the carbon that's most substituted. So your chloride ends up here, or bromide in the case. So two bromides end up here because of this bad donation between lone pairs of halogen to what is that really sp2 hybridized. Not a carbocation, a vinylic cation. But anyway, so because of this, this is more positive, so that carbon that the first halogen is on is likely to be attacked by the nucleophile, so that other nucleophile comes on and attacks the same carbon. Okay, Br2, that's what we went through. Br2, right? That was our reaction here. Cl2, whatever. You always end up adding two bromides. Oh, this is the interesting one. Okay, let's look at this one. This is a nice one. What do I have here? This, a triple bond. And I have H2O, H2SO4. So what is this really? What does the H2O and H2SO4 really give you? Anybody? H3O plus, which really is same as this thing. So that's really source of your proton, electrophile. So your triple bond, just like double bond would, attacks this. So you basically, so there's a hydrogen here. So I'm going to redraw that hydrogen, and this is my new hydrogen, and I put a plus charge there. That's alternative to this thing, which means I could put a hydrogen here, and plus charge be there, right? Primary versus secondary, and we know that this is a more stable one, right? So that's what happens. The more stable is formed. And then what next? You know this mechanism because you know the mechanism with the double bond. What next? H2O as a nucleophile can attack this, right? We attack this thing, okay. Then what do we get? We get please note that I just added water. The double bond was not used for anything, right? The double bond was here, positive charge was there, the nucleophile is attacking this carbon, and that's the new bond, but I still have a double bond left over. So the double bond didn't react yet. So this is my positive charge water, so I have to deprotonate this by other water. Why not? Because that's water, it's pKa 15, this was, less than 0. So I can deprotonate this. And at the end, I end up having something like this. OH, right? Something like that. So very similar to alkene, which is a double, pi bond attacks electrophilic proton, and then proton is added to the least substituted carbon, and then you make a carbocation. In the alkene case, in this case, it's a vinylic cation secondary. And the nucleophile, because it's in water, there's so much of this water around, because there was a nucleophile that attacks this positive charge, you make a bond now between this carbon and this oxygen. You will not deprotonate this water because it's acidic, you will deprotonate it in water. And then you end up with this, right here. And for you, I'm sure that this is okay, right? Hydrogen, oxygen, carbon, double bond, carbon. There's nothing wrong with this, right? There's nothing wrong with this? No, there's nothing wrong with it. Yes?
Is there an alkyl group belonging to oxygen?
Yes, thank you. Yes, okay. Thank you. I love this. Is there anything wrong with this thing that we formed? Yes. I was supposed to say that. It's because it's not stable. It's not stable. Actually, it's stable enough to go back. It's not that it's not stable, it never forms. It forms. It's just, once it forms, there's another reaction that takes place here. You put arrows, and you form something else. You form something more stable. This is an enol. Enol is something that has a double bond immediately attached to a OH group. So you have to have a double bond, and you have to have an OH group attached. You have to have this. Okay, double bond and OH group attached. Those are kind of requirements for your enol. And you can recognize it as enol. No matter what this stuff is around, if it's cyclic, you can always still have an enol, as long as it's OH. Hydrogen, oxygen, oxygen attached to carbon. This carbon is double bonded to something else, to another carbon. So, what do? Okay, I'll draw you the most stable one. So I think Bruce has several ways of getting to the most stable one. You can have a base, or you can have an acid to drive it. But let's drive it this way. Let's pick up this proton. So now this proton is gone. I'm going to draw the skeleton here. I'm going to draw things that don't change. So this stuff doesn't change. So I pick up this hydrogen, so I make BH. And then I take this lone pair and I make a double bond here. Oops, sorry. So I took that, I made a double bond around this carbon, and of course, what does this carbon have to do? Right here. This carbon has 4 bonds, but if I make a pi bond, can I still have another pi bond here?
No.
No, so I have to lose this somehow. And really, if you have something acidic, you can lose it to something acidic, so you end up with something like this. Could be, right? Actually, enol to this conversion can happen inside the molecule. You don't need any acid or base. But I think that Bruce suggests source of proton and then a base to remove a proton. So basically, bottom line is you have to remove this proton, make a double bond, and then break this one. So that's one way. I like internally doing it, but you can do it whichever way you want. DNA bases do it internally. What I'm saying internally is like this. I pick up this proton and I break a double bond. Everything happens in the same thing. This is still enol. And where I'm going is somewhere more stable, and that more stable is right here, right? And so this, I'm missing it on. Okay. So whichever way you want to do it. Basically, you have to pick up a proton, make a double bond, break a double bond, protonate it. Whatever way you want to do it is fine. So you went from enol to something like this. This is commonly called keto. Keto because you have a carbon double bonded to oxygen, and then you have, so that's in the center, and on the two sides of this carbonyl you have carbons with something on them. So you have carbons attached to a center carbon that double bond to oxygen. It's a ketone, really functional group, and we call this keto. Keto, and this is an enol structure. So these arrows lie very much like this. And that's why when somebody talks about this is not stable, this is more stable, hence the arrows go this way. So you have to show me the arrows on the exam or final. Do we have any questions about this specifically? Maybe I can ask you? Yes?
So it wasn't stable because it was an enol?
Yes, the enols are considered as less stable than ketones. I have another example. Let's